All right, real quick review for anybody joining us through the video. I was wrong about my email. I'll send a new When did I send that email? Over the weekend or before you guys started your unit test? Anyways, I'll send a new message to clarify. Thanks for letting me know. They added a review session and they changed the time and they didn't tell me. So 2 review sessions with, I think, with spring resources. So you'll get to see questions you've not seen before. Let's start with this question on active. And we've got some other questions on active that we'll come back to for more arrow pushing. I think, Will, you asked me about this question too, correct? Once upon a time. Alkynes. So in this question, we have a vicinal dihalide reacting with excess sodium amide. 3 equivalences would be considered excess in this. What they're saying is at least 3 equivalences, but we want an excess of it. And then heat and THF. Any idea what THF is? I put it on the board one time. You should know it. It's the house with the oxygen. How did you know that? And what is that? What does THF do for us? Polar aprotic solvent. All it does is facilitate a reaction. It just is the medium for the reaction to exist in. How do fish swim? Verbal dyslexia, you know. They need water to be a medium for them to swim through, right? Well, the same thing with these molecules. They need some solvent to swim through. That's THF. I rarely put THF on my materials because it's not really needed. If you see a solvent, it usually plays a role. If you don't see a solvent, that's because the solvent didn't really play a role. So we're really focusing on the vicinal dihalide and the 3 equivalences. Now that we have actually learned about E2 reactions in lecture, let's look at this as an E2 reaction. This is a strong base. It's not a strong base I gave you in class because nitrogen does some wild stuff, and I don't want you to just willy-nilly use amide. Instead, I want you to only use amide for these applications with alkynes. So, amide is a strong base. I've got 2 leaving groups, 2 halogens, each with beta hydrogens. It doesn't really matter which hydrogen I take first, but I'm going to take the beta hydrogen that is up here. Oops, sorry. I forgot my 2 on my NH2. That's part of my E2 elimination. Base deprotonates. CH bond forms a CC double bond, and this cascade pushes off a leaving group. That should remind you of the E2 arrow pushing that you learned last week and that you might have had to show on your unit test this weekend. Last weekend. I'm abbreviating my aromatic ring here. I have removed a hydrogen from this secondary position, so now I have an alkene. I still have my bromine here, and now I have 2 hydrogens on this front carbon. That gave me a byproduct of ammonia. Conjugate acid of amide is ammonia. Are you guys okay with the fact that I'm ignoring sodium? Because sodium is just a spectator ion. It's not doing any of the chemistry. It's just annoying. Now I have another equivalence of amide. And that equivalence of amide can do a second E2 elimination. It takes a beta hydrogen, breaks the CH bond to form a CC pi bond, and kicks off a leaving group. It's a second E2 elimination. This time it leaves me with an alkyne. That gives me a new equivalence of ammonia. But I have a third equivalence of amide. And in this new alkyne that's formed, amide is a much stronger, it is a very strong base, and the alkyne is actually a better acid than ammonia. So amide here acts as a base not to do elimination, but to do deprotonation. Again, leaving me with a new equivalence of ammonia. If I had only two equivalences of amide, I wouldn't be able to do this final deprotonation step. If I had an internal alkyne, for instance, if this step had led to something like this, a third equivalence of amide can't do anything. There's no acidic hydrogen to deprotonate. So the fact that we have excess here is to both create the alkyne and deprotonate the alkyne. And so those of you struggling to get this one correct on active, I don't know. I plugged it in on Peter's and it accepted it, so long as it looks like that. There is an option where active will let you put a radical electron on it. That would be incorrect. It's not a radical species. And if that's true, that carbon with a radical shouldn't have a negative charge. That breaks the formal charge calculation. I'll just show you guys real quick what this should look like. This should be the answer. Again, you don't have to show that C, but if you do, there's nothing wrong with it. Now at the end, what you're supposed to get is this alkyne anion and this primary alkyl halide. So this is another good review of past material being explained a little bit better now with new material. This is an SN2 reaction. Strong nucleophile, strong base. Primary alkyl halide. That has preference for SN2. Substitutes the chlorine by SN2 and leaves with a much longer carbon chain. Always, always map your carbons. Like here, 1, 2, 2 attacks 3, 4, 5, 6. 1, 2, 2 attacks 3, 4, 5, 6. Uh-oh. 5 should have been connected to 3 methyl groups. 6 and 2 others. Did you submit it?
Yeah, it's right. It's just, I don't know. I think just having that extra box in the bottom broke my brain. Gauge up on the left side under there too. I just wasn't sure how that all came together. I think my brain was so.
And what is THF doing there?
I don't know.
No. What does THF do? Just facilitates the reaction happening. It does nothing. It's the water for the fish to swim in. Yeah, these are the fish. So THF, not doing anything. That's its goal, is to do nothing. All right. Can I clarify anything else on this? A deprotonated alkyne or an alkyne anion? No, that's a dangerous assumption. Here is another dihalide. 3 equivalences can never make an alkyne anion. Why? Because that alkyne will never be terminal, so neither of the sp carbons will have an H to be deprotonated. So only terminal alkynes can even become alkyne anions. Good question. Yeah. Yes, it was. Substitution of the alcohol. So we saw that alcohols, especially even if they're chiral, alcohols can be turned into bromides, substituting their chirality, or they can be turned into chlorides, substituting their chirality, which is distinct from using HBr or HCl, where they end up with mixed configuration, both R and S, indicating a carbocation intermediate. Good. Good. I didn't have a worksheet for you guys on this either, so I never gave you these reactions in a diagram. All right. Since we are on this kind of flow of substitution and elimination reactions, I say we dive into it a little bit more and look at how to predict whether something will do substitution or elimination. Mel, I think this was your question, right? Were there any specific instances you wanted to look at? Or just in general? Okay, so if I put up a reaction, we can try and determine, yeah? First, is this reaction addition, elimination, or substitution? Substitution. No pi bonds formed, no pi bonds consumed. What reagent will allow this reaction to proceed? I'll give you a hint. It's one of these 2 reagents. Oh, that's HC, HCl. HCl. What we can see about thionyl chloride is that it leaves inversion of stereochemistry, just like the SN2 backside attack. And what we see about HCl is that it leaves both R and S chiral centers, just like a carbocation intermediate reaction, like with all of our alkene addition reactions that have carbocation intermediates. What I can see here is that I do not substitute the OH where it is, but instead I see what? A methyl group shifts. I go from having 2,2-dimethyl to 1,2-dimethyl. How can a methyl group shift? Carbocation must exist as an intermediate. So this must go through a carbocation intermediate. That means I need to use HCl. So this reaction is substitution with a carbocation intermediate. So is it E1, E2, SN1, or SN2? Do you want to explain why? Good. Only SN1 has a carbocation. SN2 has no carbocation. So this substitution must have occurred by SN1 substitution. Okay, is that a good example for you, Mel? Let's try another one. First, what type of reaction are we seeing? Elimination. Pi bond forms. What reagent could be useful in forming this product? CH3OH. If I provide CH3OH and alcohol on a secondary alkyl halide, this will give a mixture of SN1 and E1. So we could add heat to drive just the E1. Would you agree with me that E1 will give a carbocation intermediate? That's the definition of E1. First, the leaving group leaves. What's going to happen to that intermediate? It will go through a hydride shift, a secondary carbocation adjacent to a tertiary carbon. Notice that my methyl group is no longer wedged. It's flat because that carbocation is sp2 planar. Now think of all of the possible beta hydrogens. Beta hydrogen on the left, beta hydrogen on the right, beta hydrogen up above. Which of them gets me to this product? None of them. The one on the right is identical to the one on the left, which would look like this. And I think you'll agree that's the most stable alkene. It's tri-substituted as opposed to the beta hydrogen up above, which is only di-substituted. The problem is neither of these are the product I'm aiming for. So can we just say E1 off the table? It cannot be an E1 elimination. Maisie. Well, we're not substituting. No, it won't be any alcohol or water. It won't be our weak base, weak nucleophiles. Natalie? There's a good answer. So, terbutoxide, I'm going to write it a little differently than I normally do because I want you guys to keep seeing it in unique ways. Big, bulky prefers the anti-Zaitsev product. It prefers to go to the less substituted. It's also good at being a base. It's actually pretty bad at being a nucleophile because it brings so much steric strain, it can't even get close to the carbon group. So it instead opts for just grabbing a hydrogen and ditching. And it wants to grab the most accessible hydrogen. However, it does this by E2, which we say is a concerted mechanism. Everything has to happen at once. And the stereochemistry is specific. We say that E2 is anti-periplanar. My leaving group, dashed. So the beta hydrogen that it takes, wedged. This is the hydrogen that it takes, not the dashed hydrogen in the same position. So tert butoxide, it works. It goes to that position preferentially. What about this? What if I, not using a weak base weak nucleophile, but I used a strong base strong nucleophile, like CH3O-? Will that go for the orange hydrogen that's dash, or will it go for a different position? Let's say it's with heat. Yeah, down here too. This was with heat. This was with heat. It'd go for what? Go to the left? We said tert butoxide will run E2, which means that it has to be a wedged hydrogen. Is there a wedged hydrogen on this position? There's a dashed hydrogen, but is a dashed hydrogen and a dashed bromine anti to each other? Then the stereochemistry doesn't work. And methoxide, hydroxide, ethoxide are small base, strong nucleophiles. They can't get at this. So where do they go? They go to this orange one. It's the only place they can go. We're adding heat, so we're not going to do substitution. And they have to do E2, so the stereochemistry has to be aligned. So actually, it wouldn't matter if we had used tert butoxide. That'd be a good answer because we know it's going to go in that direction no matter what. But in this case, even a small base would give this same anti-Zaitsev elimination. And that's because E2 is a stereo-specific reaction. Here's one of my favorite examples of this stereo-specific and Zaitsev, anti-Zaitsev chemistry. This is the stereochemistry is specific and important. This is 1-chloro-1,2-dimethyl cyclohexane, but it's let's see, 1, 2, 1, 2, 3, backwards, R. Oh, you know what? We wanted to do chirality. Mel, is that what you meant by chirality, determining R and S? Let's do it on this one. Let's look at this position 1. Who wants to remind us the rules for determining R and S? Do you want to give it a shot? Mass of. Mm-hmm. Hydrogen, if hydrogen is present, it's always the lowest priority. So what's the highest priority on this orange carbon? Chlorine. Next in attachment is carbon, carbon, and carbon. How do you know? How do you know that this carbon to the left is going to be the next highest priority? More substituted. And that's my trick. I've not seen anybody else say that. But essentially you can say, since there's no other heteroatoms anywhere else in this chain, there's not going to be an oxygen that wins or a bromine that wins. That carbon is bonded to the next most carbons. So eventually a carbon is going to win out against a hydrogen. A carbon is going to win out against a hydrogen. So eventually the more substituted will be the higher priority. I think if we put an oxygen here, then we'd be looking at carbon, 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 no difference. And then I can say carbon, hydrogen, carbon. So at that point, this one loses. And then because this direction went to the next carbon and this direction went to the next carbon, they'd share the O together. So then the only other difference will be this has hydrogens and this has another carbon. Only if the oxygen is here. But if the oxygen was here, then it's a game changer. Let's not consider it for right now. Because we're already deviating from the main problem, which was E1, E2. All right, so position 1, position 2, position 3. Is position 4 in the back? No, so whatever determination I make here will be opposite of what it actually is. You'll be telling time from the position of the numbers, right? Whatever. So, ignoring position 4, I have rotation 1 to 2 to 3, looks anti-clockwise, which is S, and I like to put that in quotation marks and then cross it out. The actual configuration is R. You feel good on that, Mel? Can someone walk us through determining the absolute configuration of the other carbon? Yeah, let's hear it.
One would be towards the chlorine,
Okay.
and then 2 would be towards the rest of the circle because it's more substituted.
Okay.
3 would be up, and then the hydrogen would be 4.
Good.
And it's backwards, so it would be what you see.
It is as it seems, which is R. Good. The way that I started this was carbon, carbon, carbon. I don't know my top 3, but I do know position 4 is the hydrogen that's going back. After carbon, I'm looking at a chlorine, another carbon, and hydrogens. And that's it. Chlorine wins, carbon is second, hydrogen would be third. So, okay, that was an example of chirality in this context. The reason the stereochemistry is important here, when you have 1R, 2R, 1-chloro, 1,2-dimethyl cyclohexane, you can show the regioselectivity and stereoselectivity of all of your different elimination reactions. So if you guys don't mind, I'm going to redraw this so that it is legible again. there is an elimination reaction that gives you this tetrasubstituted alkene, 1,2-dimethyl cyclohexene. There is an elimination reaction that gives you this R2-methyl cyclohexene. No, R3-methyl cyclohexene. And there is an elimination reaction that gives you this R1-methyl 2-methylene cyclohexane. I'm not ever going to make you name that one. The methylene group, the CH2, it's a weird substituent. It can't be the longest chain. You can't have a carbon chain that goes between the ring and outside the ring. Okay, so this I wanted to actually give you last week. I didn't get it on the board. This is a great summation of all of the different characteristics of the E1 and E2 reactions. First, anti-Zaitsev E2. This tertiary alkyl chloride, it has 3 beta positions. Here, there's a beta hydrogen that is syn to it. Here, there is a beta hydrogen that is syn and anti. And then here, there is a beta hydrogen that has all of those positions. It looks weird to draw it out, but there are 3 hydrogens up here, so all of the positions count. If I want to form an alkene from this least substituted beta position, then I'll use tert-butoxide. Tert-butoxide prefers that less substituted carbon, and it gives us the least substituted alkene. But because my chlorine is not anti to the tertiary beta carbon, to the tertiary beta hydrogen, I can't use E2 to get this beta hydrogen. I must use E1. So I could use something like water and heat, and I can do E1. E2, E1, because it's not antiplanar, which means that my only other condition, those small, strong base, strong nucleophiles like hydroxide, they will also run E2, but they'll give a more substituted E2 than tert-butoxide. And specifically, they'll only eliminate that hydrogen which is antiplanar to it. It's full of information, isn't it? It shows you E1, always Markovnikov, always the most substituted, no matter what. I said Markovnikov, I meant Zaitsev. E1 is always Zaitsev, always the most substituted possible. E2 is anti-periplanar, meaning it's only Zaitsev if it's possible. And in this case, there is one E2 that is more substituted and one E2 that is less substituted. Tert-butoxide will always only go for that least substituted position. I forgot a methyl group. Thank you. Anybody else notice where that methyl group missing is? Which product is it on, Yoon? Yeah, that was an important methyl group. Thank you. Tetrasubstituted, tri-substituted, di-substituted. Yeah, otherwise they would have both been di-substituted. Mel, do we need more practice with E1, E2, SN1, SN2? We didn't do a lot with the substitution. That's actually a good point. Where did we start with all of those? What do you guys notice? What do you try to do? Yeah. Look to see if you have your anti-Zaitsev base or a Zaitsev base. Tertiary. Good. Identify the substitution of the alkyl halide. Primary, secondary, tertiary alkyl halide. And then you compare that against your table. And you bring that table with you onto the exam, and you can just look at what combination of those base and alkyl halide you have. Okay. Do you guys want to see more on identifying SN1, SN2? Okay. Are we good on chirality? Do we need more review deciding if a compound is chiral, achiral, or meso? Yeah? All right. I think now is a good time to talk about that. You know, I have to see if I can find this file. A while ago, maybe more than a year ago, I wrote up a final exam prep guide that actually gave you prompts about things to show and didn't give you any chemical reactions, no chemicals. It would say something like, show a meso compound that has 2 reflected chiral centers. Show a substitution reaction that creates an ether. Show a chiral molecule that has at least 3 chiral centers. And it was just prompts, no necessarily one right answer that you could go through. I'm going to see if I can find that and send that out to you guys, because the process of creating your own ideas helps stir the creativity in a bit of a different way. It's a good exercise. Chiral, achiral, or meso? And with that projector off, it's so quiet. We have a civil war, a divide in the class. Raise your hand for chiral. Raise your hand for achiral. Oh, the achirals have it. Who wants to explain? Good. No carbon is bonded to 4 unique groups. There's a carbonyl. That's only bonded to 3 groups. One of them is the oxygen. It's bonded to twice. And then there's a quaternary carbon that's bonded to 2 methyls. Might as well be 2 hydrogens. They're 2 identical groups. Achiral. Good. Chiral, achiral, or meso? Chiral? 2 more agreements? Another. These guys were on the winning side last time too. You want to prove it? What do you think? Why is it chiral? How many chiral centers does it have? Just one? Where? In the center. That's the only carbon that's not attached to two hydrogens. CH2, CH2, achiral. But this has a CH2 phenyl, a CH2OH, a hydrogen, and a phenyl. Chiral. Sorry, I should have maybe done a better job with this. All right, let's look at its structural isomer. Chiral, achiral, or meso? Already got one vote for meso. Is it the definite textbook meso compound right there? Oh, you want to check with a neighbor? Meso? Remember, a requirement for meso, it's two chiral centers that are symmetric to each other. How many chiral centers here? None. Ooh, this is a good compound, huh? And it's not even that complicated, right? 1,3-diphenyl 2-propanol. You could name that. The carbon in the center is bonded to two CH2 phenyl groups. There's symmetry right here, which means there's no chiral carbon in the molecule. Achiral. I tricked you because you thought I was going to give you a sample of all three of them. Okay, do another. Chiral, achiral, or meso? Chiral. All right, let's do a structural isomer. Chiral, achiral, or meso? Meso. Oh. Yeah? Do you know what I mean? Right? Isn't that fun? I gave a talk the other day. Maybe a few of you were at that, and I made them move their arms like they were absorbing energy through their bonds. Anyways, that's kind of how I feel sometimes. I'm not meso. Not meso. Chiral, because those two chiral centers do not reflect through each other. Yep. Chiral. All right, well, let's do an example of something that is meso. Good goodness. Don't know why it's slanted. That was weird. What functional group is that? Andy? That's an epoxide. Good. Chiral, achiral, or meso? Yes, and it's very hard to make them both wedge. So let me give you a compound you could actually make that would have two things that were wedged. How could you make that? What? Diol addition. Have an alkene precursor, OSO4, diol addition, syn diol addition. Which reminds me, I think I had a problem in the active that showed you how to do an anti-diol addition from an epoxide intermediate. I gotta try and remove that. So this one was chiral. This one is meso. This one, you sure I'm not tricking you? Because I've been known to trick you a few times. Can you prove it that it's meso? What does it have that makes it meso? 2 chiral carbons and a plane of symmetry. Both of the carbons bonded to the epoxide have 4 distinct groups, and they are symmetric to each other. Good. Mm-hmm. Yes. It has to have at least 2 to be meso, because the chiral centers need to reflect into each other so that the molecule at large is not chiral. It needs to be an even number, which is to say that sometimes a position might seem like it should be chiral, but actually it's not, because it's where the plane of symmetry runs. For instance, if we expanded this one that I gave you before, oh, I didn't actually expand it though. If we expanded it so that the 2 phenyl groups were actually creating chiral carbons, and then I have that OH, once again, it feels like that OH carbon should be chiral, but that is where the plane of symmetry runs. And by the way, this structure, it's not chiral or meso. There's not enough information. We don't know if one phenyl is wedged and the other is dashed. We don't know if both are wedged, both are dashed. That'd be the same as both being wedged. So this is a problem where there are many stereoisomers, one that is meso and 2 that are chiral. And we don't know which we have. We don't have any right now. So there's not actually enough information here. This is chiral or meso, unsure. This one, meso. No, racemic is when you have a 50-50 mixture of enantiomers. I don't know. I don't know how they were made. There is something in organic synthesis labs called enantiomeric reagents. Enantioselective reagents, not enantiomeric. Enantioselective reagents generally themselves are also chiral. And so they interact with achiral things, like an achiral alkene, in a specific way, because it itself is chiral, and that means that it preferentially forms one specific stereoisomer. So, for instance, if I wanted to make this compound, and I was using this to do it, oh, no, this is a bad one because it's meso, so it's not racemic ever, because meso compounds have no enantiomer. They are their own mirror image. If I wanted to make this compound, what reagent would I add? Sorry? NaBr? Sodium bromide? Oh, NaNH2? No, if I wanted to go from this alkene to this bromine, sodium amide would kind of go the opposite direction, but it would only do one elimination. Br2 to do alkene addition. Yeah, I would never ask you to show THF on the test, but on active, you would be familiar to seeing it Br2 with THF. No, you don't. The only time you need to specify a solvent is when the solvent plays a role in the reaction, right? So if this was Br2 in water, that gives us the halohydrin addition. That water is actually the solvent. So your question, are these racemic? Okay, this reaction would form this enantiomer and the other enantiomer selectively. But if I had some other reagent, and I don't know if there exists a reagent for this reaction, but if I had some other reagent that could interact in this reaction in a specific stereo way, that it only ever created this stereoisomer and never the opposite stereoisomer, then I could synthesize that enantiomer 100%, or, as the major product, which means it would not be racemic. They wouldn't form 50-50. When you see a chiral compound, you don't know if it's racemic or not, unless you know how it was made. If it was made in a way where the odds of the enantiomers are 50-50, then they form 50-50. If you are just given a compound, not racemic at all, it's just that compound. It's a good question. By the way, I want to remind you, I tend to not take breaks during the review periods. So if you want to take a break, feel free to excuse yourself and get up and move around. I know that can be a little challenging when I just go and go and go. Okay, how do we feel on chirality now? Should we move on? Good refresher. I kind of want to take this idea of chirality and segue into chairs, except Mel wanted to talk about chairs, so I think I'll wait for Mel to get back. Maybe now is a good time to do those problems on active with the arrow pushing. Can you remind me, were they the last ones? I see them now. Before we even look at what it wants us to draw, why can't I zoom in? Are you not able to zoom in on active? What the heck? Okay, I wanted to zoom in, but actually let's go back to analyzing SN1, E1, SN2, E2. Based on the reagents that we have here, what would we expect to be the reaction that proceeds? 1-bromo, 1-methyl cyclohexane with water and heat. What type of reaction are we expecting? E1. Tertiary alkyl halide, weak base, weak nucleophile, heat. The first two pieces of information tell us competition between E1 and SN1. The heat tells us preference, temperature control, for elimination. What is the first step of a first order reaction, whether it's SN1 or E1? The first step Well, I guess it depends on what you mean by elimination. The leaving group leaves. That's the first step. You could call that bond dissociation, right? Actually, some people just call that first step dissociation. The alkyl halide dissociates. Elimination is generally what I consider the formation of the pi bond, and that doesn't happen just yet. Okay, so the leaving group leaves. What is the leaving group? The bromine. When it leaves, will it leave behind the bonding electrons with carbon, or will it take electrons with itself? Why? It's greedy. It's big too. More electronegative. Not by a lot, to be quite honest, but by enough. So the bromine takes the electrons. These electrons now belong to bromine. Leaves me with a carbocation and a halide and water. By the way, this plausibility of what happens in a real scenario, doesn't it seem like these two things should reconnect? Sometimes they do. They just fall back together. That's that whole idea of a reaction coordinate diagram being traversable in both directions. Sometimes the reaction reverses itself. Now I have a carbocation. I actually have two nucleophiles, and I have two weak bases. But we know that we were aiming for E1. So in my second step, what should I show? Oh, by the way, I have to look for carbocation rearrangements, right? Second, tertiary carbocation, will that rearrange? In OCHEM 2, you might spend a little bit more time learning that it will rearrange to something allylic for sure. Or it might rearrange to something benzylic, absolutely. But tertiary, surrounded by secondary, that's not benzylic or allylic, no rearrangements. How do I show the elimination step? Break one of the CH bonds and point it at the oxygen. Take oxygen's lone pair and bond it to one of the hydrogens. Does it matter which? It does not, because this is not stereospecific. It's not anti-periplanar. This is going on with a carbocation. Now that I'm stealing hydrogen, good. And isn't that a terrible confusion? It's not a hydrogen bond, which of course is an intermolecular force. It's a bond to hydrogen. And this is why we shouldn't have hydrogen bonds, so that we can use it in this context. We should call it extremely strong dipole interactions, not hydrogen bonding, because that's what they are. Good work. CH electrons, those are owned by carbon. C owns the CH electrons. And who else to share those electrons with but its next door neighbor who needs electrons? So you satisfy the carbocation and you form the alkene. Done. Question. When HBr is mixed in water, do you know what they form? H3O plus and Br minus. Which means that if you have this setup, you are well set for an alkene addition reaction, HX addition. HX addition sees the alkene as a base, which forms a carbocation on the most substituted position before a halide does a nucleophilic attack. So when I said earlier that this energy diagram is traversable in both directions, we're looking at an equilibrium reaction. We're looking at dehydrohalogenation, which is in equilibrium with the reverse hydrohalogenation. So if you were to do this in lab, it's not as easy as every molecule running to the alkene, because some of those alkene molecules then run backwards after they've formed. You might be limited on your yield. Yes and no. HBr is a very strong acid. The pKa of HBr is lower, more negative, than the pKa of hydronium. So hydronium really exists more than HBr. We say HBr is a strong acid, which means it completely dissociates.
So even though we have like
they're not really doing this because you have a strong acid and a weak base versus a weaker acid and a weaker base. Yeah? That's just an issue of pKa's. Not the type of pKa's that I'll have you guys rank, by the way, because this is something that's hard to guess. Why is H3O plus a weaker acid than HBr? It's not because of charge, that's for sure. We typically say things that are more positive are better acids. That's not true here. Is it because of atom? The oxygen is more electronegative, but it's much, much smaller. This is one of those unintuitive pKa differences. It's one that you get familiar with over time. Does that answer your question? All right. Peter, was there another one on the arrow pushing you wanted to look at? Yeah. This is 22. Yeah, so you see THF is written on the arrow, which means ignore it. It's just there to facilitate everything. They gave you this pleasure of showing the spectator ion, sodium. They give you a lot of options here, don't they? They show a lot of carbon-carbon bonds that can cleave. Carbon-carbon bonds do not like cleaving. That takes a lot of energy. They show you that your nitrogen can attack, your carbon can attack, your CN pi bond can attack. Let me ask this. When cyanide, Cn- is a nucleophile, both atoms have a lone pair. Which atom is a better nucleophile? The carbon with its lone pair or the nitrogen with its lone pair? Which atom is a better nucleophile? Carbon? You agree? Why? Less electronegative, more willing to share. That's the definition of a nucleophile, someone that's good at sharing electrons. Carbon is less electronegative, better nucleophile. So carbon donates, also it wants to get rid of that negative charge, doesn't it? Carbon donates its electrons to the carbon, forcing off the chlorine. Should this be an SN1 mechanism or should it be SN2? I mean, it's set up so that it only happens at once. But based on our conditions, SN1 or SN2? Strong nucleophile, Cn-, weak base, which means it prefers SN2 above everything else, and primary alkyl halide. Primary alkyl halides are not good at forming carbocations, so it's not going to want SN1. Plus, this is driving the attack. It wants to come in and bond. So it's forcing it to be second order. Both chemicals are involved in that rate determining step, SN2. Okay. All right, let's look at chairs. Back up to the top of the list. Have we talked enough about the carbocation rearrangements yet? Or do you guys still want, we saw them in a couple of problems. Do you guys still want to see them a little bit more directly?
Understanding.
Or just like the shifting as well, like when.
When it should be hydride and when it should be methyl?
Yeah, just like if we saw a reaction with that.
Okay, we'll do that in a little bit then. Okay. Chairs. Oh, I wanted to segue chirality and chairs. Let's look at this compound, chiral, achiral, or meso. Meso has a plane of symmetry that bisects the ring. Now let's see which of the chair conformations is the most stable. So a reminder on drawing chairs. I'm not going to ask you to draw chairs on the final exam because I don't want to grade them. But they can be useful in helping yourself understand something. So draw two diagonal lines. Should they be perfectly on top of one another? No. Make them offset. And preferably offset the bottom line backwards. I know that sounds a little weird, but if you offset the bottom line forward, you're not able to get quite the right shapes. Offset the bottom line. On the downside, connect by an up V. On the upside, connect by a down V. Or just, in other words, a normal V. How many up carbons? 3. How many down carbons? 3. Now we'll draw the same one. I know active got really picky with you guys about making sure that your carbons switch positions, but in actuality, as long as you move your substituents, it doesn't matter if your rings have the same shape or if they're mirrored. It is so not important. Doesn't matter where we start, so long as we move consistently. So I want to put this carbon here, which means that my other chiral carbon will be clockwise relative to that. Up OH on an up carbon takes what position? Up axial, straight up. What else is connected to this carbon? Sorry? In what position? Down, equatorial. The up position on this carbon is already claimed. So now it has an equatorial group that's actually a little bit down. Then my next OH is up on a down carbon. What position does it take? Up equatorial. If it's up, then it's up, then it's up, then it's stuck. Leaves you with a down hydrogen. Do you see the plane of symmetry? You shouldn't. This is not the conformation that has that plane of symmetry. Doesn't it kind of look like this? Those OH groups don't reflect into each other. They're not both up axial. They're not both up equatorial. One is axial, one is equatorial. They're not symmetric to each other. Okay, let's do the other one. Where do you want to move the dotted carbon? Do you want to move it clockwise or do you want to move it counterclockwise? I'm going to move it clockwise. Doesn't matter. So now my dotted carbon is here, and I'm still need to go clockwise to my other carbon. An up carbon became a down carbon. Up axial becomes up equatorial. A down carbon becomes an up carbon. Up equatorial becomes up axial. Is that the conformation that has symmetry?
Oh, no, I wasn't looking at the chair as a whole. I was looking where I was looking between the H's and between the OH's.
Like here.
Yeah,
I can see if you put it at an angle like that. The problem is the rest of the ring then will be at kind of a weird twist. This is also not the conformation that has symmetry. It's actually a lot easier to know that a molecule is symmetric from the top-down view. Know what conformation is symmetric? Its boat conformation has symmetry. And where does the boat conformation lie? Is it higher in energy, lower in energy, or equal to these chairs? Higher. This is a transitional conformation between the boats. And it doesn't matter. As long as that compound has symmetry in any one of its conformations, it is always meso. That's all. We saw that with linear chains like this. Not a symmetric conformation, and yet it's a meso compound. Because when you rotate around one of those bonds into a higher energy conformation, it ended up being meso. All right. That was the segue I wanted to use from chirality into chairs. But the question now is, which of the chair conformations is higher energy? Is what? Is lower energy. Yep. Maximum equatorial groups, minimum axial groups is lowest energy. Axial groups cause axial strain. They just have steric strain with other groups on the top of the ring or the bottom of the ring. Cause steric strain. Yep. Axial groups cause twice as much steric strain. Equatorial groups don't. So for every axial group, you get more strain than any equatorial group. Yes, correct. So for any of these OH groups, Br, methyl, ethyl, whatever. So which chair is higher energy? They're the same. One axial, one axial, one equatorial, one equatorial. These are equal in energy. All right, let's do the same thing here. Let's look at the high and low energies for 1-bromo, 4-tert-butyl cyclohexane. Once again, it does not matter where you put them, right? So long as you are consistent, especially when you rotate. So I'm going to put tert-butyl up here on my carbon number 1. When I go into my second chair conformation, I'm going to move that position clockwise so that it's down in the corner. I like my corners. Tert-butyl, up on an up carbon takes what position? Up axial. Bromine, up on a down carbon, takes what position? Up equatorial. Now I flip them, and I get up equatorial and up axial, tert butyl bromine. Which one is higher energy? How do you know that tert butyl is bigger than bromine? Molecular weight, ooh. CH3 times 3 is 45, plus 12 is 57. Tert butyl weighs 57, and bromine weighs 79, 51% of the time, and 49, or 80, 49% of the time. So bromine is actually very heavy. But steric strain is not about weight. It's about the size, the surface area. And bromine is just one atom. Tert butyl is 14 atoms, 13 atoms. Tert butyl is a ton of atoms and a ton of bonds. So tert butyl takes up a ton of space. Imagine if we didn't show this as tert butyl, but instead we showed it as all of these CH3s with all of their bonds coming out. Which one looks more bulky now? Yeah. You can see why TBU is a really nice abbreviation now too, right? Imagine if I made you show that with all wedges and dashes. Maybe that'd be an extra credit. Be a boring extra credit. So this is a lower energy conformation. Okay, here's another fun fact. This comes back to relate to E2. Bromine here in an up equatorial position is not anti with the beta hydrogen. Equatorial bromine and beta hydrogen are not anti. We could prove it by looking at the Newman projection through the ring. But we would see that they're both in equatorial positions. Despite the fact that this is up and this is down, they're both in equatorial positions. And in order to be anti, they'll need to both be in axial positions. So this is the conformation of this molecule that is reactive to E2. The conformation on the left, unreactive to E2. I want to take a stereoisomer rather than cis 1-bromo 4-tert-butyl. I want to look at trans 1-bromo 4-tert-butyl cyclohexane. And I'm going to look only at the conformation that is reactive to E2. Couple of questions for you here. One, is the conformation on the right the high energy conformation or the low energy conformation for trans 1-bromo 4-tert-butyl cyclohexane? Is this the high energy or the low energy conformation for this trans stereoisomer? High? Were you going to say low though? Okay. Oh, I'm sorry. It's flipped. Was that a confusion for more of you? I've flipped it upside down. This is a or not a meso. This is an achiral compound though. So if I actually just took this whole molecule and rotated it like a basketball, I would have a down bromine and an up tert butyl. So I'm actually just I'm looking at it up to fix the confusion. Still the trans isomer. I've just flipped it like a pancake. Yeah, didn't mean to throw you off like that. This agrees better with the top-down conformation. Both were accurate. One was just more confusing. Is this the high energy conformation or the low conformation? Why? Andy, do you want to explain why? They're both axial. In the other conformation, they must both be equatorial. So this is the high energy conformation. Okay, these two stereoisomers, they give the same product during elimination. They give the same alkene, and I know I've got that issue again of my tert-butyl being upside down, but it flips around. They give the same alkene. Here's my question. Which stereoisomer requires less energy to form this alkene? Which stereoisomer forms this alkene with the lowest energy transition state? Both are equal or no way to know. B has a lower energy transition state, easier to get to it, easier to get to this alkene. I'll say that again.
Higher energy, right?
It's what?
Higher energy.
And so it has what?
You need less energy to put into it to react with stuff.
But you said it's higher energy. I need to get it to that energy before it can react. If this is reactive to E2 and it's the higher energy conformation, that means I need a lot of energy to be able to make this compound in this conformation in order to do E2. No, you got it on the head, which is most people will say it's already at a higher energy, so it'll do it just fine. Where did that energy come from? I had to put that energy in to get it into the high energy reactive conformation. Compared to this, which will prefer its low energy conformation, and that's where it's reactive. So to try and put this into a diagram for you, the trans stereoisomer needs to get up pair conformation before it will react by E2. So here's the E2 reaction. Here's its reactive conformation. The cis stereoisomer is already in its lower energy conformation before it goes on to do the E2 reaction. So it takes less energy to get over that activation barrier. I've tried testing on this so many times. I've tried putting in the homework. I've tried doing a lot with it. It's a confusing question. But it's interesting, which is if they can both make the same product, which one will make that product more readily, more easily? Well, whichever one makes the product from a more stable starting point, because that's where it's more likely to be at any given time. It's unlikely that it would ever be over here at a higher energy. Okay, we got about 9 minutes left. this good on chairs? Yeah? Oh, I already crossed it out. Great.
You accidentally crossed. You were supposed to cross it.
Yeah. No, I didn't mean to cross out error pushing. I think it's because I had decided to move on to chairs. I think maybe we save some more of the carbocation rearrangements for Wednesday, as well as pKa. We can really easily knock out degrees of substitution. How many of you still feel a bit confused with degrees of substitution? Yeah, okay. It's something I'm actually trying to work on the wording for, because I've been trying to clarify for you degrees of substitution of a carbon, substitution of an alkene, versus substitution reactions, right? These are our categories. I don't even actually, that's not how I want to represent it. Methyl, primary, secondary, tertiary, and quaternary. Degrees of substitution of a carbon. What's our definition again? The degrees of substitution of a carbon are defined by how many carbons it's bonded to. So let's look at some methyl groups. These are carbons that are not bonded to other carbons. Methane is a great example, our smallest hydrocarbon. Methanol is a great example. I told you guys about methanol. Don't drink it, right? You die from it very easily. We also have things like methyl halides, methyl iodide, methyl bromide, methyl chloride. Very, very good electrophiles. They have low steric strain. Electrophiles. And then I think this kind of like flips it on its head, but this is a compound called methanal, otherwise known as, I wonder if you guys know. Not carbonic acid. That would actually have two OH groups. Good guess? This is an embalmer. Formaldehyde. I know. Formaldehyde systematic name is methanal. It's not bonded to any other carbons. It's just a one carbon aldehyde. Primary means you're attached to one other carbon. So ethane is a great example. This would be our smallest system of primary carbons. That gives us things like methanol. Methanol is a primary alcohol as opposed to a methyl alcohol. I could have one bromoethane. That's a primary alkyl halide. And how about this chemical? It is a carboxylic acid. Its name? Ethanoic acid, a two-carbon chain. So it's a primary carbonyl. This specifically is acetic acid, vinegar. Secondary compounds. I'm going to skip to bond line now. Secondary carbons bonded to two other carbons. So good examples here. Let's expand it. This is cyclohexanol, a secondary alcohol. Here we have, it'd be 1-chloroethylbenzene or 1-chloro-1-phenyl-ethane, secondary alkyl halide. And then, of course, I can look at secondary carbonyls. This is cyclopentanone. The functional group there, ketone. on the tertiary substitution is the last degree of substitution that I'm able to find functional groups. So let's look at isobutane or 2-methylpropane. There's a good example of this is tert butoxide. That's the conjugate base of a tertiary alcohol. We could also look at 2-iodo-2-methyl butane, tertiary alkyl halide. There is no tertiary carbonyl. A carbon bonded to 3 other carbons can't make another double bond. And then, like I said earlier, quaternary can't have any functional group. You can't have a quaternary halide. That's because your carbon has already consumed all 4 of its bonds to other carbons. So why do we call it degrees of substitution? What has been substituted? Maybe. Could we say that methane is not substituted? It doesn't have 1 degree of substitution. It doesn't have 2 degrees of substitution. It has 0 degrees of substitution. And what is it that methane has completely? Hydrogens. So when you substitute a hydrogen for a carbon, but that's the important part. It's not a hydrogen for anything. Because substituting a hydrogen for OH didn't change its substitution. For a halogen, for a carbonyl, didn't change its substitution. So it's just changing its bonds for carbons. That's how we decide. So now you know. Okay, good? Okay. All right, I hate ending early. So how can I torture you for 30 more seconds? Elliot. NaCC. Oh. Yeah, do you want to draw its bond line structure? Na plus CCCH3 minus.
Okay. Yeah, I was trying to figure out whether it was from
What unit was, what section?
on the most recent one, I think.
Good, I'm right there. Yeah. Oh, goodness, you can't see anything though, can you? So NaCCH3 is just a very dumb way the propyne nucleophile, the propyne anion. That's what it is. It looks scary, doesn't it? It's not. It's not that scary. It's just abbreviating a triple bond. So what type of nucleophile is that, by the way? Is that a strong base, strong nuke, strong base, poor nuke, weak base, weak nuke, or strong base, weak base, strong nuke? It's actually a strong base. Yeah, its pKa is 25, which we would consider to be a strong base. pKa of O minus, alkoxides, which we also call strong bases, has a pKa around 15. So this is a stronger base than alkoxide. It's a carbon group. So On the low end, carbons are acidic at like 25. That's the alkyne. Or in the 40s, that's the alkenes. Or in the 50s or above, that's the alkanes. So carbons in general are strong bases. The only carbon that's not a strong base is cyanide. And that's because nitrogen pulls on that negative charge and helps stabilize it a lot better. And it's primary, which makes it's sp hybridized, which makes a big impact too. So this first step, substitution of the alcohol, stereospecific. You get inversion of the alcohol with a chlorine, followed by strong base. It doesn't tell you low temperature, and we agreed that this would have competition between SN2 and E2, but given the fact that it wants you to show this, it doesn't really care if it's substitution or not. If you tried drawing the E2, it wouldn't accept it. Therefore, it must be asking for the SN2, and SN2 also gives inversion of stereochemistry. So if you invert and then invert, you get retention. The stereochemistry at the final product is actually the same as the stereochemistry of the starting material. Yeah? And actually, there's one thing I want to put you guys onto. Oh, I took you way over. I'll talk to you about it. It's about roadmaps on the final exam. And that, I think, we'll kind of talk about with multi-step synthesis. Because I know you haven't seen them a lot in class or on active. So I'll talk about those before we see them on the final exam. All right, guys. Thanks for your time. I'll see you on Wednesday.
If they have a question about the 17 of the active one. Yeah,
This one?
because there are two major products that is asking about using the heat. So this one is actually the SN substitution product. So got confused. Yeah, I tried a lot. Why it keeps showing this substitution results? So I don't know.
That's a good point. I don't know why it's asking for that.
Yeah, it's this one. I tried this one and this one asking another one, right? So I thought, is there other ways for the carbon alliance to rearrangements, and it doesn't allow that.
So it wanted elimination
Yeah.
and substitution.
Yes, the substitution. Finally, I see. Oh, okay, maybe try the substitution, and then it accepts. So I thought, yeah.
Okay. Thank you for letting me know. I will look into that.
No problem. Thank you.
And I'll think about maybe pulling that one out.